Okay, so in this video, I'm going to do about half of your homework problems for you. You are going to be assigned 1 through 15 on the packet that you have, and I'm going to do the evens, you're going to have to do the odds. So, not only do you have those exercises and the answers at the bottom, but what you also have are a bunch of pictures to refer to. So please use those pictures when you're trying to not only understand my sloppy drawings on this thing, but to help you with your drawings and really what the math represents. This unit is very geometrical, meaning it follows a lot of the rules that you're learning in geometry and shows how those rules are governed by the equations that we're working with. So they are there to help you. Please refer to them repeatedly throughout every single problem. Alright, so let's start out with number 1. I'm not going to do it for you, but I am going to tell you that the picture on figure 17.6 should help you with that one. It will make it very easy on you if you look at that picture, and it will make sense why the answers are the way that they are. So I want you to understand your answer, not just have it on your paper. Alright, moving on to number 2. What you need to do in number 2 is first identify the important information. That's what you've had to do all throughout the year with these types of problems. So a fish lies 80 centimeters below the surface of a clear pond. So we're working on exercise 2 here. Now the reason why we're using O instead of D is because pretty much everything in here is measured in distances. So this object, in the case of the fish, lies 80 centimeters below the surface of a pond. So if the index of refraction of water is assumed to be 1.33 and that of air is approximately 1, then we know that the symbol used to represent the index of refraction is n. One of our n's is 1.33. and the other one of our n's is just 1. Question is, which is which? So, before we answer that question, let's figure out what question we're being asked. How far below the surface does the fish appear to a person looking down from above? So we want to know, what does the image distance look like? And we represent that with an I. Alright, so I'm going to do my best to draw a picture representing what is going on here. But let's say that this is the land, this is the water, and I have a person here looking down at a fish. So here's where the fish actually is right here. And there's light coming from the sun going into the water, but we'll forget about that. We're just going to talk about the light that leaves the fish after it's reflected. Now, when light moves from water, which we know here, this has an index of refraction, and air has an index of refraction. When it leaves the water, it bends, and what it bends is further away from the normal here rather than closer to, because it's going into an area with less materials to interact with. So it's going to appear as if the fish emerges, or the fish is at a position that's actually higher up because of the way that these light rays are bent. When light rays get bent, our brain still thinks that they're moving straight. So it appears to us like this fish is somewhere that it is not. And that's why you have those mirrors. Objects are closer than they actually appear in cars, because of the way that light changes its direction when it interacts with different surfaces of different indices of refraction. So we could say, W for water and A for air. That doesn't really make sense though. Let's talk about the sequence. It's first in the water and then it leaves the water to go into the air. So it would make more sense to label these based on the chronology of the light passing through each. Okay, so we're going to give a subscript 2 for air and 1 for water. Now to the equation. The distance of an image is based off of the product of the object's distance multiplied by the ratio of the indices of refraction. Okay, so 2 over 1. 2 is higher than 1. Think about it like that. But you'll be given this equation. The thing is, you'll probably have to manipulate it to find this, this, or this, not just this. Alright, so this is an easy one. We're just plugging in our numbers into this equation. Over here, up top, we have 1. And on bottom, we have 1.33. So it's really just 80 divided by 1.3, which is equal to about 60.15 centimeters. And we're going to go ahead and round that to 60 centimeters. I'm doing that here because you will have to do it on your next problem. The reason why we're rounding it like this is because one of our original measurements was only to the ones decimal place, not to the tenths or the hundredths. These right here are given, so they're not measurements. So whenever you have measurements and you're dealing with them in math, the number that you end up rounding to is based off of the precision, or the one with the least precision of your measurements. This is not stuff that you're going to be tested on, but it's stuff that I taught you at the beginning of the year. So it's important to know for that first college, or that first physics course in college, where they will gloss over it quickly without any assumption about whether or not you understood. Okay, so moving on. Let's get a new layer. Number 3, you're doing the same exact thing, except for you're going to be solving for I instead of for O. Number 4, we're really just doing the same thing. An insect is embedded inside of a glass block. So this glass block has an index of refraction of 1.5. And the insect is located 2.4 centimeters below the plane of the surface. So that's where your object is located. Now, how far does the insect appear to a person looking at the block? So we want to know what it looks like to an outside observer. Now we're missing a piece of information here. We know the equation to find the image distance is equal to the product of the object's distance and the ratio of the indices of refraction. But we're not given the, well, let's say if the light's reflecting off the bug, we're going to treat this as N1. We're not given N2. Now the fact that we know that this observer seeing the image is a person, we can assume that N2 is air, because people breathe in air. It doesn't say that this person's looking at it in scuba gear underwater. So we'll just assume that N2 is 1. I'm not going to have you make any assumptions like that on your test, but if you do have to make any assumptions like that on your homework, just analyze the problem and think about what would most likely be true, and then see if your answer matches up with the answer key. That's why I gave it to you. Okay, we already have everything we need. The object is 2.4 centimeters away. N2, the air, where the observer is at, the second media that the light's traveling through, is 1. And the index of refraction for the glass is 1.5. So 2.4 divided by 1.5 gives us about 1.6. Or not about, gives us 1.6 centimeters. Okay, easy enough. 3 is just like the last two, except for you're going to have to solve for I. This should be easy. At this point in the year, I expect you to be able to do this, but really all that's happening, these two are flipping positions, and these two are flipping positions. You could write that down right now, but just make sure that you understand the algebra. That's the easy stuff for this homework. Okay, now to the tough stuff. All right, before we get on to number 6, and for those of you that are just fast forwarding through this, trying to get the answers easily, are going to miss this, and you deserve the struggle that you put yourself through. Number 5, I want to tell you, there is an image. Oh, and for the last problem, or the second to last problem, there's a good image. 17.9 will help you with the fish one. But for number 5, 17.6, that figure will help you with the drawing. So those 3 lines, those are the ones that you want to worry about. The one that starts off straight, the ones that ends up straight, and the one that goes straight the whole time. That's going to help you understand how images gets formed when they go through these simple lenses. The one that we're about to do is more like figure 1717. So let's get to it, but for number 5, use figure 17.16 to help you with your drawing. If you're listening to this, hopefully that'll make it easier on you. So 6 says a positive lens has a focal length of 12 centimeters. Just to let you know, positive, what that means is that it bubbles out. So it's concave lens. I'm not going to use the word positive on the test. You will only see it here on this homework. But for these purposes, just know positive means convex, bubbles outwards. So it has a focal length of 12 centimeters. And the object is located at a distance of 3 centimeters from the lens. So the first thing that we want to know, letter A, is how far from the lens is the image? We want to know the image distance. So there's a new formula coming your way. The focal length, or the inverse of the focal length, is the sum of the inverse of an object's distance. Wait, let me make sure I write this down correctly. Yeah. Plus 1 over the image distance. So this should remind you of the formula for equivalent resistors when they are in parallel. Hopefully you remember how to work that algebra. It's not too bad, especially if you've already done it a bunch of times. So we're solving for I here. So let's go through the painful algebraic process one time, and then the rest of the time you want to refer to this process. Sometimes you have to solve for F, that's a lot easier. Sometimes you have to solve for O, it's just as hard as what we're about to do. So I'm trying to solve for I. First thing I would suggest you do is get rid of this 1 over O. And this is object, not 0, you can't divide by that. So subtract by 1 over O on both sides. And what you end up with next is that the inverse of the image distance is going to be equal to 1 divided by the focal length subtracted by 1 over the object's distance. Okay, here's where it gets a little rougher. What to do here? Leave myself some space. Now, a lot of us right now might think, I'll just plug in the numbers and then deal with it then. That's fine, you can make it work like that. If these two have a common denominator, which they do, you could jump straight to the arithmetic, but I want to show you how to do it with the algebra. Now, the basic problem is that these two are not necessarily going to be the same number, and in this case they aren't. So what we need is a common number between these two. So in this case, they do have a common denominator, but if they don't, all you have to do is multiply them. So if I want to multiply O by F and F by O, I could, but then I'm going to change this top number. I'm going to change the whole fraction. If I don't want to change the whole thing, I have to multiply it, not just by O, by O over O, because anything multiplied by itself or divided by itself is just 1. So you're not really changing the fraction, you're just changing the way that it looks by multiplying it by a big 1, or a number that is essentially equal to 1. It just has more than 1 on the top and the bottom. Now over here I have to do the same thing if I want this to be OF, or the product of O and F. You multiply it by F divided by itself on both sides. So you can see it gets a little messy. This is the only time we're going to go through it. So this is O times 1, which gives you O, minus F times 1, which gives you F. And then the bottom, you have O times F. Okay, so this is almost the what we're solving for. So this right here, this is the inverse of the image distance, but we want the image distance. So there's a couple ways that we could do about this. Some of you might be, oh, I can cross multiply. Yeah, you could do that. It's not really going to make your life that much easier. There's still 2 extra steps. I could go the long way, bring this over here, bring this over here, bring this back down over here. Instead, I'm going to show you a little trick that I've already mentioned multiple times. If you take a fraction to the -1th power, essentially what you are doing is inverting that fraction, or just changing the denominator with the numerator. So I'm changing this to I over 1, which is really just I, because anything divided by 1 is itself. And I take this numerator, put it into the denominator, take this denominator, put it into the numerator. So that, I think, is the best way to do your algebraic manipulation when you need 2 fractions to be flipped around. The only thing I have to emphasize is this only works if you have no other terms. Like if it's 1 fraction, you can't have like 1 over I plus something or minus something. It's got to be just all be hooked together through division like this. Okay, so now we're ready to plug in our numbers. O, 3 centimeters. F, 12 centimeters. Down here, 3 centimeters minus 12 centimeters. So I put this denominator in parentheses so that you know you have to do this division before, or this subtraction before any division. Okay, so 12 times 3 is 36. And 3 minus 12 is -9. Oh, I messed up there. This is centimeters times centimeters, so it's centimeters squared. So 36 divided by 9 is 4, but this is 36 divided by -9, so that gives you -4. The square centimeters cancels out with this centimeters down here, and you get -4 centimeters. That's your image distance. That takes care of A right here. A lot of algebra to get to there. If you want to try to memorize this equation, feel free. But I think it's more important that you know how to get from this to that. That's really what you learn, is the process. Memorizing this will be gone before the end of the next unit. Okay, so that takes care of A. Now let's move on to B. Is the image real or virtual, or rect or inverted? So there's some information here that gives us an idea, but instead of just looking at that, I want to refer to the picture on figure 1717. So what you're looking at there is what I would draw in letter C. I don't think I want to try to do it because, you know, it's hard enough to do on the whiteboard, but with this software, I don't think it would be useful for me or you to even see. So I'm going to write C figure 1717. All right, now let's talk about B. Is it real or virtual, inverted or upright? So, I'm sorry, it says erect. Erect just means standing straight up, so I say upright to avoid the unnecessary chuckles, but feel free to enjoy the word. So, that image is standing straight up. It's erect, and it is virtual. The reason why it's virtual is because there are no actual light rays coming from that source. If you look at all of those dotted lines, those are dotted lines that represent what it appears to the observer, what it looks like those lines are coming from. None of them actually come from that source, that image in the back, but they appear to come from that point because of how our brains perceive light. We know that it goes in straight lines, so when it gets bent, our brains try to create an image of where it would be had light traveled in the straight path that we know that it's supposed to travel through. So for B, and then there's actually another thing that helps you figure that out. Since the object's distance is smaller than the focal length, that means that this object is going to be virtual and upright. So I'm going to justify my answer. Since, and we can see it up here, O is less than F, and there's another thing, our image distance is less than 0, not O, but 0. This is erect and virtual. Erect just means it's oriented in the same direction as the actual object, and virtual means that light does not actually diverge from that point, but it appears to because of the way that our brains understand things. So I'm not going to try to draw this. See figure 1717. If you were listening to me before I started this problem, you know which figure to refer to help you with your drawing of figure 17.16. But just to relieve many of you, you won't have to do drawings like this on your quiz, but they do help you get a better understanding of the math that will be on your quiz, which will definitely involve this equation. You will all have to do something like this to get to something like this. All right, moving on to number 8. Number 8. Oh, real quick, before I forget, number 7. There's a mistake in your book. That, or I can't figure out the mistake that I'm making. But number 8, your book says that the answer is, I don't know, 3.43. 5.3 seems to be the answer. I mean, I've plugged in the numbers in online calculators on multiple websites, and I always get this answer. So change your answer. In the book, I believe it says 3.43. That is wrong. This is what you should be able to generate from your own process. All right, so number 8. What do we have here? A negative lens. So last time positive lenses, those were convex. This time negative lenses, these are concave. Has a focal length of negative 10 centimeters. That's why they call it a negative lens. An object is located 20 centimeters from the lens. What do we want to know? Well, in A, we want to know where this image is at. So this would be the equation that you want. The inverse of the focal length is the sum of the inverse of the object distance and the image distance. Okay, so I'm not going to go through all that algebra again. If you need a reminder, go back to the last part of the video that hopefully most of you watched. And we end up with the image distance is equal to the product of the object's distance times the focal length divided by the object's distance subtracted by the focal length. Alright, so we have negative 10 multiplied by 20 all divided by, no, I flipped these two around. So this actually belongs here and this belongs here, but you know the order of multiplication doesn't matter. What matters is that I get it right down here. 20 centimeters minus 10 centimeters. Alright, so I'll put this whole thing in brackets to help keep myself from making a silly mistake. Alright, so over here, negative 10 times 20. Think about it as negative 2 times, or 2 times negative 1. You get negative 2, and then just attach those two zeros onto the end. Negative 200 centimeter times centimeter is centimeter squared. Divided by 20 minus negative 10 is the same as 20 plus 10, which is 30 centimeters. So this square centimeter cancels out this centimeter. Negative 200 divided by 3, well, this 0 cancels out this 0, so it's like negative 20 divided by 3, which gives us negative 6.7 centimeters. So that's where this image is located. Now, for B, since this, what are we working with? A negative lens with a negative focal length and an object whose distance, or which has a distance, 20 centimeters. I believe there's a figure that we can refer to rather than just have you take my word for it. Okay, let's see here. Alright, so everybody take a look at figure 17.19. Okay, that's not the answer, but that will help you understand the answer. So what we have there is an object with a distance that is longer than the focal length. Now I know that our focal length is 10 here, and that probably gives it kind of away. What that means is that you're not going to get the light rays to emerge or to converge on the other side. They can only appear to emerge from the side that the object is on. But we do see in that picture that we have an image that is virtual because the light rays only emerge from the actual object, and it's upright or erect because it's oriented in the same direction as the actual object. So whenever you have objects that are further than the focal points for negative lenses or concave lenses, then we're going to have virtual and upright images. But really all you need to do is see, okay, look at your eye here. It's a negative number. So for B, since I is less than 0, this image is virtual, meaning no light rays actually come together to form it, and it's erect, meaning it's standing in the same direction as the actual object. That's true when you're dealing with lenses, but not necessarily mirrors, which we're going to move on to next. So please analyze figure 1719, and hopefully it helps you understand how when you have objects further away from the focal length of a concave lens, you will form upright or erect virtual images. Okay, number 10, moving forward. A concave mirror has a focal length of 12 centimeters. So concave, that means it curves inward. An object is located 6 centimeters from the surface of the mirror. All right, that's it. A, how far from the mirror is the image of this object? So we want to know what the image distance is. Now, even though we're dealing with mirrors, which reflect instead of refract light, we can use the same exact equation that we've been using. The inverse of the focal length is the sum of the inverse of the object's distance and the object's image. So jumping straight to the end of the algebraic process that we already went through 2 problems ago, the object's distance multiplied by the focal length, all divided by the difference between those 2 distances, will tell me where it appears this object is relative to where it's actually at and where the focal point is at, or the length of that focal point from the center of the mirror. Okay, so we have 6 centimeters. Multiplied by 12 centimeters divided by 6 centimeters subtracted by 12 centimeters. Okay, 6 times 12, that's 72 square centimeters. Divided by 6 minus 12 is negative 6 centimeters. 72 divided by 6 gives us negative 12. This cancels out with that. Negative 12 centimeters. Okay, so that takes care of A. Now we need to deal with B. Is the image real or virtual, erect or inverted? So we might jump straight to saying it's a negative image. That means we have, so that means that we must have it an erect and virtual. But instead of just jumping to trying to memorize something, let's analyze figure 17.21 and make sure that we understand why that can work in this case. So this is A right here. For B, we can use a lot of the same justifications that we already made. Since the object's distance is less than the focal length, and the image distance is less than 0, then this image is, so let's take a look, figure 17.21. I have an object located closer to a mirror, a concave mirror that curves inwards than the focal length. since my object distance is less than my focal length, the image is going to be virtual, meaning it appears as if those three lines emerge from the point, and upright or erect, meaning that the flame is pointed in the same direction as both the object and the image. So just look at those lines. It should be obvious why they curve the way that they do. Line 1 reflects back into the focal point because it starts out moving straight. Line 2 reflects straight in a straight line relative to the center line because it appears as if it emerged from the focal point. And then line C reflects back in the same direction it came from because it hits at a right angle, so it doesn't bounce up or down. It just goes right back to that point C, which is known as the center of curvature. Anything passing through the center of curvature will hit an object at a right angle, or will pass back through the center of curvature if it hit the mirror at a right angle. Alright, so this image you can see is virtual and erect. Okay, pushing forward, just two more. We're working on number 14 now. Okay. So number 14, the objective lens of a microscope. Wait a second, I'm sorry, number 12. A convex mirror has a focal length of -10 centimeters. So I made a mistake. This is not 14. This is 12. So convex mirror, this means it bubbles outward, has a focal length of -10 centimeters. And an object is located 10 centimeters from the surface of the mirror. So that's where the object actually is, 10 centimeters from that surface. Surprise, surprise, what are we supposed to find first? The image of this object, how far away it is. And we always start with this equation. You know, if that first time I showed you how to manipulate this was difficult for you, do it every time you use it. The more times you practice this, the more likely you will know how to do it on the day of the quiz. So, the image is going to be equal to the product of the object distance times the focal length divided by the difference between those two distances. So our object is 10 centimeters away from the surface of the convex mirror. The focal length is -10 centimeters away from that convex mirror. Convex mirrors are just like concave lenses in that they do the same thing to the light. They diverge it, which is why this is a negative value. Okay, and then down here we have 10 minus 10 centimeters minus -10 centimeters. All right. So 10 times -10 is -100 centimeters. And 10 minus -10 is 20 centimeters. I made a mistake up here. Centimeters times centimeters is centimeters squared. Okay, 100 divided by 20, -5. This cancels out with this, -5 centimeters. Okay, so B, is the image real or virtual, upright or inverted? So And then C, trace 3 rays from the top of the object to confirm your numerical results. So I'll tell you what, instead of jumping straight to B, let's look at a figure to help us understand the answer for B. So being that we have a negative value, let's make sure that our rules still apply. But everybody, take a look at the image, or I'm sorry, figure 17.24. What you have there is an object in front of a concave mirror, and what you see there is an image being formed that is upright or erect and virtual, meaning that there are no actual rays coming from it. So in this case, let's just use, since I is less than 0, the image is virtual, meaning light rays don't actually come together at that point, and erect, meaning it's oriented in the same exact direction as the actual object. So hopefully you're seeing something common between convex mirrors and concave lenses, especially with all the images. A negative lens, they call it, or a concave lens, is pretty much only just showing you virtual upright images, and the same thing goes for convex mirrors. You're only going to be seeing virtual upright images. Now, when it comes to positive lenses or convex lenses, you can see real and inverted images, and you will see them in the problems that you're doing on your homework. And it's important that you do those problems because you may not get experience with something that's going to be very similar on your quiz unless you do the rest of the homework. So we only have one problem to do. But before I finish this, let me just point out C figure 1724 here is what I meant to do. So on your other problems, I want you to be able to identify which of the figures that we didn't go over can be used, but you can guarantee that I didn't put them on there for decoration. They are there to help you, especially for these types of problems. Okay, last slide, last problem. Number 14. 13 and 15 are just like 14. These ones are not that bad. They're probably the easiest ones of the bunch. Okay, so an objective lens of a microscope has a focal length of 0.4 centimeters. So let's not worry about objective lens right now. Let's just write this lens has a focal length of 0.4. Is it centimeters or meters? Yeah. Okay, and the object in the microscope slide is placed at a distance of 0.5 centimeters from the lens. So there's your object distance right there. 0.5 centimeters from the lens. Okay, so 14. At what distance from the lens is the image formed by the objective lens? Okay, so we have a focal length, we have an object's distance. Of course, they ask us for the image distance. Okay, so at this point, most of you can memorize this formula. OF minus O minus F. or divided by. So let's do that one more time real quick. 0.5 centimeters times 0.4 centimeters divided by the difference, 0.5 minus 0.4. All right, 0.5 times 0.4, 5 times 4 is 20, so 0.5 times 0.4 is 0.02, or 0.2. No, 0.02. Yeah. And this will be 0.1. Multiplying decimals, not my finest. It is 0.2, arg. So forget about this here. Okay, so 0.2 divided by 0.1 gives us 2 centimeters. All right, so this is the old stuff. Here's the new stuff. The magnification. Very simple formula. Magnification, the formula for it, I believe I put it on that packet. It's so easy. All you have to do is divide the, so this is how much something gets magnified is going to be the ratio of the image and the object, but you need to have a negative sign in front of there. So how much this object is going to be magnified is going to be based off of the negative value of 2 centimeters divided by the object is 0.5 centimeters. So 2 divided by 0.5 gives you 4, or negative 4. So negative 4, let's try to make sense of that answer. What distance from the lens is this image, the magnification of this image? So this object is magnified times 4. I know you might think, oh, if it's a negative value, that must mean that it's getting smaller. No, it's getting larger. I think the negative value is just has to do with whether or not it's being flipped upside down or not. If it's not flipped upside down, then this is negative, which cancels that out to make the whole thing positive. But since this is flipped upside down, anything that is a positive I means it has been inverted. We didn't see that today. But if it's positive and this is negative, a negative number means that it's an inverted magnified image. So if it was a fraction, then you know that it would be smaller. But in this case, since it's an integer, this object got 4 times larger. So you could use this to figure out how much larger something is. Like if it started out at 1 meter and it was magnetized by 4, or I'm sorry, magnified by 4, it would look like it was 4 meters. Okay, so that's it. We're done with the time. Make sure you get through 1, 3, 5, 7, 9, 11, 13, and 15 on your own. All right, have a good weekend.